All right, so today's lesson, we are going to learn about what are called heating and cooling curves. I'm going to show you guys kind of what these look like. So these are graphs that show heat and temperature, usually. So it's not like a time and temperature like you would kind of assume. It's actually amount of heat and temperature. So we're going to be looking at ways that we measure that amount of heat, and we're going to be doing some calculations in regards to these heating and cooling curves. So to start, we need to know what enthalpy is. So enthalpy is something we're going to be getting into a lot more in our next unit, but it is important for phase changes and phase transitions. So it's important concept for states of matter as well. So enthalpy is signified by this delta H. So delta H, or triangle H, means change in heat, basically. So this is the total heat content of a system. Basically, a good way I like to think of it is it's the internal energy of the system. So it's basically another way to think of it is heat needed to induce change in phase. So it's how much heat is needed to kickstart a phase change or a phase transition. So it's how much heat is needed to go from solid to liquid, or how much heat is needed to go from liquid to gas, or how much heat is needed to be taken out to go from gas to liquid, or how much heat is needed to be taken out in order to go from liquid to solid. So very important way to think of it is heat needed to induce or start a change in phase. There is an overall equation for it. So we've got Q. Q means energy. So Q is our energy. So our amount of energy is equal to N, which is our number of moles, times our enthalpy. Enthalpy is usually going to be a constant, and this would be given to you. So this is something that would be given to you, a given number in the equation via a chart or on like an equation sheet. So this is always going to be given. So I wanted to show you guys some common enthalpy numbers that you would have access to if you were taking like a quiz or a test in here, as well as worksheets. So there's different heat needed or heat contents or enthalpies for different steps or different phase transitions. So enthalpy plays a role during phase transition. That's very important to note. It's during a phase transition. So it's not while something's heating up or cooling down, it's while it's changing phases. So that's very important to note about enthalpy. You only use it when things are changing phases. So for example, we have vaporization and condensation. That's a phase change. Melting and freezing, that is another phase change. And then our third phase change would be sublimation or deposition. Sublimation is going from it's going to go from solid straight to gas. Deposition is going from gas straight to solid. So sublimation is like dry ice. Deposition is like how frost occurs. So first we're going to look at vaporization and condensation. Basically, these things are opposite, or the values for these things are going to be opposite. So our enthalpy for condensation, COND is how we represent that. Our enthalpy for condensation is going to be equal to the negative enthalpy of vaporization. And I have this written down right below here for you. So the number is going to be the same. It's just going to be negative for vaporization, and it's going to be, it's going to be negative for one of them and positive for the other. Vaporization includes adding heat. So it's going to need heat because we're going from liquid to the gaseous or vapor state. So more heat is going to be needed, or more kinetic energy to get the particles moving faster to break those intermolecular forces. So heat of vaporization is going to be positive. The value for enthalpy of water to vaporize is 44.01. The unit is going to be kilojoules. That's a unit for energy per mole. So we've got 44.01 kilojoule per mole. Condensation of water is taking heat out of a system or taking energy out of a system. So that one's going to be negative. So we've got negative 44.01 kilojoules per mole. Like I said, these numbers would be given to you on a quiz or test. These are not things that you need to memorize. What you do need to know is that condensation and vaporization are equal to the negatives or opposites of each other. Melting and freezing is another one. Melting is known as fusion. So sometimes people, or you'll see in worksheets or on quizzes and tests, it'll say enthalpy of fusion. So melting is known as fusion. So when that happens, we're taking something that is in a very rigid structure, and fusion is going to allow it to be in that more flowing structure, but still have IMFs holding it in the liquid state. Our equation for the state change is enthalpy of freezing is equal to negative enthalpy of fusion, FUS, otherwise known as melting. Our enthalpy of fusion for water, and these are both for water, just so you know. So our enthalpy of fusion for water is going to be 6.01 kilojoules per mole. So that's how much heat is required to melt ice, basically, per mole. To freeze it, we need to take out negative 6.01 kilojoules for every mole of water. Like I said, these numbers would be given to you. And the last one we have is sublimation and deposition. So our equations for state change, deposition is equal to negative enthalpy of sublimation. Basically how we find these is this little equation here. So from going from solid to liquid, that's fusion or melting. Going from liquid to gas, that's vaporizing. So the way that we do these is we're going from solid to gas. So that means what we're going to do is we're going to add our fusion and our vaporization because we are skipping the liquid state. So for example, for water, if we were to look at water, we're going to take water's enthalpy of fusion, which is 6.01, and we're going to add that to its enthalpy of vaporization, which is 44.01. And these are both kilojoules per mole. So 6.01 plus 44.01 equals 50.02 kilojoules per mole. That would be our enthalpy of sublimation of water. Obviously, our enthalpy of deposition would just be negative of that. All right, so that's a little background on heat needed to start or kickstart a phase change. So that's all that enthalpy is how much heat is needed to start that phase change. Now we're going to look at heating and cooling curves in a little bit more in-depth cycle. So heating and cooling curves. Basically, heating and cooling curves have an equation, and they're going to be very mathematical. So it's not just graphical, it's also going to be mathematical calculations. These are going to be quantitative, so we're not just looking at a trend, we're actually looking at numerical numbers in chemistry for this. So there's another equation that we use for heat being released or absorbed when something is being heated or cooled. So this is no longer when something is going through a phase change, it's when it's being heated or cooled. So it's as we're approaching phase changes. And that equation is Q equals mc delta T. Q we know is energy. So we're always talking about this in terms of energy because remember, temperature is actually a measure of kinetic energy. M is going to be our mass. How much of something do we have? C is going to be specific heat. This is a constant and it will be given to you. This would always be given to you. And obviously delta T is going to be our change in temp. Something that's important to note, heating and cooling, or this equation for being heating and cooling, does not apply to phase changes. You only use this equation when we are heating or cooling something. This is going to make a lot more sense when we're looking at our heating and cooling curve. So I'm going to go ahead and flip my sheet over, and we are going to look at our first heating and cooling curve. Okay, so this is a heating and cooling curve. We have temperature in degrees Celsius on the left side. Heat added, this is going to be kilojoules. usually on our x-axis. So we have a few different states happening here. When we have a flat line, that is a phase change. So flat lines equal change in phase. Angled lines are going to equal heating or cooling. Angled up equals heating. Angled down equals cooling, obviously. So looking at this, this is a heating and cooling curve for water. So the water starts at negative 10 degrees Celsius, and it is getting heated up until it reaches 0 degrees Celsius. So we have heating. Once it's at 0 degrees Celsius, it's going to stay at 0 degrees Celsius no matter how much heat is added until all of the solid melts. So it's saying here at this flat line, we've got solid ice and we have liquid water. So think of this like a glass of ice water. Once all of the solid melts at this point, that's when we're going to see the increase in temperature happen again. So we have more heating. At this stage, our water is liquid. Once it reaches 100 degrees Celsius up here, the liquid begins to boil. When it's boiling, we've got gas, water, and we've got liquid water. It's going to remain at that temperature until all of the liquid has evaporated, which is at this point. When that happens, we're going to have only gas, water, and it's going to begin heating again. So these areas that I'm going to highlight in yellow are going to be our phase changes. So we have two phase changes in this instance. I'm going to write that in like a green color. So we've got phase change and phase change. Melting. We're going from solid to liquid. This is going to be fusion. Liquid to gas, this is going to be vaporization. So those are kind of the two phase changes we're looking at in this heating and cooling curve. All right, we're going to use this heating and cooling curve to kind of help us out with how we actually calculate amount of heat. So our example problem, it says total heat needed to change temperature and phase for a substance. The question asks us, how much heat is required to convert 135 grams of ice that start at negative 15 degrees Celsius into water vapor at 120 degrees Celsius? So our starting temperature is negative 15 and our ending temperature is going to be 120. So some things that we know about water. We know that water is going to, at STP, is going to melt at 0 degrees Celsius. So we know it melts at 0 degrees Celsius, and we know it boils at 100 degrees Celsius. Some things that are given to you: heat of fusion, heat of vaporization, specific heat of ice, specific heat of water, and specific heat of steam. The reason that these are important is because those specific heats are that letter C from our equation before. So we got to write out our steps. What you do is you write out your steps. You talk about your heating or cooling, and then you also talk about phase changes. So we're starting at negative 15 degrees Celsius. So our first step is we need to heat from negative 15 to 0 degrees. So we're going to heat, and that is going to take our negative 15 degrees Celsius all the way to 0 degrees Celsius. In this instance, we are heating. Okay, so remember heating, if you look back at the first page, we have phase transition and we have heating and cooling. We're going to be using this equation, Q equals MC delta T. We need specific heat, and we're going to need specific heat of the state of matter that we're in while we're heating. So if we're heating ice at negative 15 degrees Celsius, our specific heat that we're going to be working with is going to be the specific heat of ice. So 2.09 joules per gram times degrees Celsius. Okay, once we've heated and we've reached 0 degrees Celsius, we need to have a phase change. So we are going to melt our ice. When we melt our ice, that is a phase change. or phase transition, we are going to be working with heat of fusion. So in this instance, we're going to be using heat of fusion, and that is 6.01 kilojoules per mole. Our third step, we need to heat again. So we're going to heat from 0 degrees Celsius to 100 degrees Celsius. Remember, this is heating. In this instance, we're in the liquid state. We're working with specific heat. So we're going to write for our specific heat, we've got 4.18 joules per gram degree Celsius. Once we've reached 100 degrees, we're going to vaporize. When we're vaporizing, that is a phase change. At that phase change, we are working with heat of vaporization or enthalpy of vaporization. That's 44.01 kilojoules per mole. We're vaporizing until everything is changed to steam. And then our last step is we are heating one more time, 100 degrees Celsius to 120 degrees Celsius, because that's what our question is asking for, 120. At that instant, we are at steam. So we're going to be working with the specific heat of steam, which is 1.84 joules gram degree Celsius. So that's our first thing, is to write out the steps that we need that are occurring in our phase change. Step number 2 is determine the equations that you need. So you're going to look at each one of these steps and you're going to input an equation for them. Remember, if we're heating, we're working with Q equals mc delta T. If we're working with a phase change, we're working with our enthalpy equation. So our first step, we have Q equals mc delta T, and this is when we are in the ice, so when we're heating our ice. Step 2, we're melting our ice. This is a phase change. So we're going to have N times, which is our number of moles, times our heat of fusion. Step 3, we're heating. So we're going to have mc delta T, but this one's with water instead of ice because we're in that state. Then we vaporize. So we've got our number of moles times our heat of vaporization. Our very last step, we're heating our steam to 120 degrees. So we've got mc delta T of steam. So this is the equation that we're going to plug these numbers into. So I'm going to go ahead and flip my sheet over. A good way before I do that to kind of keep track of these when you look back at your notes is to write out those numbers there for you. All right, the last thing that we do is we plug and chug. It's important that we keep track of what is a joule and what is a kilojoule. So notice that specific heat is in joules and heat of fusion is in kilojoules. It's important to keep track of that, and you'll see that on the next page. So plug and chug, and you want to make sure your answer is in the same units. So that's why I said check out joule and kilojoule. All right, so Q total is going to be equal to our amount of heat needed, or amount of energy needed. It's going to be equal to our very first equation, which was mc delta T of ice. So we've got our mass. Over here, it said 135 grams of ice, so that is our mass. So we're going to have 135 grams times our specific heat of ice, which was 2.09. This one is joules, so that's why I'm writing a J underneath of it. Times our change in temperature. We went from negative 15 to 0, so our change in temperature is 15 degrees. We're going to add that to our fusion of ice. We need to figure out number of moles. So remember, moles equals mass over molar mass. Molar mass of water, we're just going to be really easy, 18 or 18.02. So 18.02. So we're going to take our mass, which is 135, throw that over 18, and we're going to multiply that times our heat of fusion of ice, which is 6.01. Remember, the heat of fusion for ice is in kilojoules. So underneath this, I'm just going to write kilojoule to kind of keep track of my energy unit. Next, we heated up our water. So we have 135 grams of water now, times our specific heat of water, which is 4.18. That one is joules, times our temperature change. Our temperature change is going from 0 to 100 degrees, so our temperature change will be 100. I write a joule under here because heating is in joules, phase change is in kilojoules. So kind of a nice way to remember that. Next, we are going to boil our water. So we're going to take our mass, which is 135 over 18.02 to get our number of moles. We're going to multiply that times our heat of vaporization of water, which is 44.01. The unit or energy unit for that is kilojoules. So that's why I'm writing a kJ under there. And then the very last step that we're doing is we are heating our vapor to 120. So 135 grams of vapor times the specific heat of water vapor, which is 1.84. That one is in joules. Times our change in temperature. So we went from 100 to 120, so our change in temperature is 20. So for this, I've got joules and I've got kilojoules. We're going to keep track of that as we do these calculations. So the way that I like to do this, and I write this out in kind of different steps, I like to figure out what these numbers are in my parentheses. So my Q total is going to be, I'm going to calculate this number, and this gives me roughly 4,230 joules. Remember, that one's in joules. Plus my second parenthesis, I'm going to take 135 divided by 18 times 6.01, and that gives me roughly 45. My unit for this one is kilojoules. Next, I've got my third set of parentheses, 135 times 4.18 times 100. That is going to give me 56500. Unit is joules. Fourth, we're working with kilojoules, moles times our heat of vaporization. That's going to give us roughly 305 kilojoules. And our last one, 135 times 1.84 times 20 gives me 4,970 joules. We've got joules and we've got kilojoules. I like to have everything in kilojoules. I don't really know why that's my preference, but it is. And it's really easy. So we're going to convert to kilojoules. And the way you do that is you move your joules decimal place 1, 2, 3. So we're going to have 4.23 kilojoules. This one stays the same, 45 kilojoules, plus 56.5 kilojoules, plus 305 kilojoules, plus 4.97 kilojoules. Add all of that up, and we end up getting an answer of 416 kilojoules. We're going to look at example problem 2. I know that this was a lot. Obviously, you're going to have access to your notes for your test and everything for this. We're going to do a lot more practice tomorrow in class. But we're going to look at example problem 2. So this wants to know how much energy in kilojoules, so this one's being specific to us, it's telling us in kilojoules, will it take to completely vaporize 200 grams of 25 degrees Celsius water. So this water is starting at the liquid state, and it's starting at 25 degrees Celsius. We have 200 grams of that water. And so we need to first write out our steps. So what do we need to do? We need to heat our liquid water. So we're going to heat it, and that's 25 degrees Celsius, and we need to heat it to 100 degrees Celsius. We're heating, and we're working with liquid water, so we're going to use the specific heat of liquid water, which is 4.18 joules gram degree Celsius. Once we've reached 100 degrees Celsius, at that point, we are going to need to have a phase change. So we're going to vaporize. In that instance, we're using our heat of vaporization, which in this instance, they tell us is 40.7 kilojoules per mole. Completely vaporized, 200 grams. At this point, phase change is what's going to be how much it takes to completely vaporize. It doesn't ask for anything above that. So we just started at 25 and we want to completely vaporize. So this one's easy. It's just 2 steps. We have to heat and then we have to have a phase change. So next we need to write out our equations. So our Q total is going to be equal to our heating, which remember heating is the MC delta T. So we have MC delta T, and that one is for water, plus our enthalpy. And that one is moles times heat of vaporization. Third thing that we need to do is we just plug and chug. Our mass is 200 grams. Our C, which we wrote down over here, is 4.18. Remember, joules, we write that underneath. Times our change in temperature. So 25 to 100 gives us a change in temperature of 75. Plus our heat of vaporization. We have number of moles, so we're going to take 200 and we're going to divide that by our 18.02. Times our heat of vaporization, which in this instance it tells you is 40.7. Unit for this one is kilojoules. I like to do my parentheses first. So in this instance, for my parentheses, I've got 62700. My unit for this one is joules, plus 452.2 kilojoules. We want everything to be in the same units, and the question specifically asked for our energy in kilojoules. So I'm going to just convert this one quickly to kilojoules. 1, 2, 3. So we're going to have 62.7 kilojoules plus 452.2 kilojoules. That's going to give us our Q total of 514.9 kilojoules of heat are required to completely vaporize 200 grams of water that started at 25 degrees Celsius. We're going to do more work with these and more guided practice together tomorrow in class. So hopefully this helps, and hopefully this is going to be something you can use to study from and use.